Hi, this is Mr. Merrill with another circular motion quantitative type problem. So in this problem we have a pendulum that instead of swinging in an arc vertically, it's swinging around in a circle. And the question is, given this length and this angle, what is the period of rotation, as in how much time does it take to complete one circle? So we start out by drawing a force diagram. The one issue some of you might have is the fact that look what I've called the positive r direction. So I'm saying that the positive r direction is the direction that points towards the center of the circle. Now, for those of you in Dr. Hall's class who may be watching this video, you may have not talked about that, and this isn't going to be as applicable to you. So I'm calling the positive r direction towards the center of the circle. The positive z is whatever you want it to be, up or down, but I mean, why not call it up? And then we take this angle of the string, right? So we imagine this tensional force along the direction of the string, and that angle there between the vertical and the string must be the same as the angle here, because of you have basically two parallel line segments bisected by this line here, and you can see those two angles are congruent. So anyway, once we have that geometry down, we can break our one off-axis vector into components, and notice that even though it's not accelerating up or down, it must be accelerating towards the center of the circle. That's how it's getting redirected. So these two z-axis components are congruent, but we have this leftover r-axis component that provides us a net force, and therefore an acceleration to redirect the ball around the circle. The next thing we do is write out the vectors in component form. So it's a little bit different. So instead of having the x component and then the y component, here you'll notice we have the r component and then the z component. And I think the tricky thing is right here is resisting the temptation to put this as a negative, because you say, ooh, this component, it points to the left. But you have to remember it's pointing in the positive r direction. So this is a positive r component. Otherwise, it's pretty straightforward. You just have to resist that temptation and note that you're using a different coordinate system. So once you have the components, it's the same as always. You set up two equations. You decide which direction is their acceleration and which direction is their not. In the r direction, we have acceleration, so we'll set that equal to the mass times the acceleration in the r direction. And z, we don't. We add up the components and we generate two equations, the same starting point for every force problem. Then we think about what we're looking for. We say, okay, at the end of the day, I need to somehow relate this to the period. And the period's going to be somehow related to the acceleration. So I can imagine a substitution where I take these z components, rearrange them in terms of ft, and then substitute into this ft over here. You can see once I've substituted this into the ft here, there's a little bit of simplification I can do. The sine over cosine becomes a tangent, and there's a mass on each side. So that we see the acceleration in the radial direction is very nicely simplified to the strength of gravity times the tangent of that vertical angle. Now we can relate that acceleration in the radial direction to some things like the period and the radius. So substituting in this relationship, we can do a little rearrangement, some algebra to solve for the period. And then you say, ooh, I know all these things, except for the radius. So here, we need to do a little bit more geometry. We recognize the right triangle that the string makes with what we would call the radius, the distance between the center line and the mass. And we can set up a ratio. The opposite side divided by the hypotenuse has to equal the sine of this angle here. Rearranging to solve for r and then plugging in those values, you find that the radius must be 0.05 meters if the length of the string is 0.1. Anyway, we plug that in and we get a value for the period that interestingly does not depend on the mass and only depends on the angle, the radius, and the strength of gravity. So just keep in mind of the things that are slightly different than your other force problems, namely that if we're going to use the positive r and positive z-axis, that's going to change things up, and recognizing what substitution do I need to make here. There's not a whole lot of options. You're either trying to relate it to the speed or the period, and that's going to change your problem solving a little bit there. Alright, I hope that was helpful.